Hey guys, this is Zach Orlove coming to you live from Brown Building, Colorado School of Mines, here to present for EEGN 307 Feedback Control Systems final project. Let's go meet the team.
Sara Fuhr.
Hi guys, I'm Chmura.
And I'm Ciccareli.
Alright, because we have so little energy storage, we need to make sure the feedback loop controls the power in to the turbines to equal the power out. Because we don't have a lot of storage, so the energy generated needs to be used right away.
Because the system is constantly changing in terms of the load required, the turbines always need to adjust the frequency to match 60 hertz.
So the system in question that we chose to model was the turbine itself. And this system will be governed by the differential equation shown here, 2h omega dot plus d omega dot is equal to power mechanical minus power load. Now essentially this governing differential equation for the turbine comes from essentially force equals mass times acceleration, but the angular version of that. You have the polar moment of inertia J times the angular acceleration is equal to torque. In order to simplify the analysis of this differential equation, we have to perform some normalization. And what I mean by that is in these two power terms. This PM term is the mechanical power, and its value is going to be from 0 to 1, with 0 meaning no power, and 1 being full capacity. Essentially, this PM term is the fraction of the total capacity of the grid that we're at. And this PL term is the load power. And it's also normalized from 0 to 1 to reflect the total percentage of load that we could possibly be at. In a perfect world, this difference between mechanical power and load power would be 0. And the grid frequency would always be at 60. But in the real world, this load term is always fluctuating, and we need a feedback control system to cope with that.
Okay, so as you've seen before, through the different algebra, this is the open loop transfer function. And we had to decide what our H value is and what our D value is. H is the physical inertia of the turbine spinning, and D is the dampening that we put onto that turbine. So we consulted a power engineer here at the Colorado School of Mines named Dr. P.K. Sen, and we said the best is to have the inertia to be as small as possible, which in our case is 4, and the dampening to be as high as possible, which is in our case 5. So when we put a step response, this is what it looks like. This is bad, because the normalized frequency should be at 1, which we normalized to equal 60 hertz. Since it's now currently settling at 1.2, that's no longer 60 hertz, bad for the grid. Also, the rise time and settling time is way too slow, so we need to change that with the controller.
Alright, so I'm going to be drawing our block diagram for our system. We're going to start with R of S, which is our generator power, and that is going to feed into this sonic circle, which is going to output E of S, which is our error. Now ideally this would be as close to 0 as possible. This then goes into our feedback control, which is C of S, and that comes out as our mechanical power, PM. That's further summed with the PL, the disturbance, and goes to G of S, which is our generator. And finally, once that is looped, that will come out as omega S, which is our system frequency. And based on any of the disturbances, we will choose the KD and KP, which are values for settling time and percent disturbance, for our feedback controller, which is a PD controller. Now, our primary control goals for the system are to get omega s to follow r of s as closely as possible, which is our grid frequency. To do this, we can take any value for r of t equals a times u of t, where a is any scalar that is necessary. Our second goal is to minimize the percent overshoot and the settling time, which is done through our feedback controller. Finally, our non-critical goal is to reject as much of the disturbance as possible. This isn't crucial to the system, but the less disturbance we can have, the better.
Right, here's the root locus for our open loop transfer function. And we only have one pole on our left-hand side, and by definition, since we don't have a right-hand pole, this is BIBO stable.
So our initial evaluation of the controller selection stipulated that we'd use a PD controller to meet our original goals. But after some analysis, we found that we would have to redesign the controller to be a PID controller in order to make the system second order, such that we could meet our goals for the rise time and settle time. Now, in order to select then KP, KD, and KI, we used three types of analyses. One, we decided to do some final value analysis. We decided then to follow up the final value analysis with the steady state error analysis. And then in order to perform the final selection, once the results from these two analyses were found, we decided to do transient response analysis. Now, in our final value analysis, we found that the final value of the response of the frequency of our system was actually going to approach the value of the steady state, of the input of the step function's magnitude. We found that the final value of omega s was going to be equal to this constant a out here, which was good because that's essentially our primary goal, was to keep consistent with the grid's frequency. The steady state error analysis showed us that the error as t approached infinity was going to be equal to d, damping coefficient, times the magnitude of the frequency input, the step response, divided by ki plus d, same damping coefficient. And this analysis led us to a bit of intuition as to what to select for ki. In order to reduce the steady state error, we wanted to make ki as big as possible. So that helped us to move into the steady state error analysis, where we essentially used the following equations. T settle is equal to 4.6 over zeta omega n, and T rise equal to 2.2 over omega n. And essentially by solving for these equations and using the governing transfer function shown previously, we were able to select the proper Kp, Kd, and Ki.
From all the analysis we did previously, we found that our Ki value would be 8,712, our Kp value to be 470, and our Kd value to be 10. So, to make sure everything's stable in our transfer function, we went to the Bode plot. And from the Bode plot, we went to the Nyquist plot. And since the Nyquist never goes around -1, and we have no unstable loops, the function is stable, which is a good thing. This is our closed loop transfer function without any disturbance. as you can see, we have a very short rise time, a very short settling time, and the settling value is 1, which, as we said previously, means that the grid is at 60 hertz. This is a very good thing because we want the grid to stay at 60 hertz, and this is without any load. So if we change it to half of the load, we get close to the same value. This is a good thing because the rise time is, again, very fast. Steady state is also at 1, which means our controller takes that load and then makes sure that the lasting frequency is at 60 hertz. And in a worst case scenario where the load is 0.99, which creates the biggest difference, we get this transfer function. This again looks very similar to our transfer function without any load. And again, the frequency is at 1 or 60 hertz, which is a good thing, which means that our controller makes the system very robust. Go.
Alright, so to wrap this up, we were able to meet all of our constraints and goals enumerated in the beginning of the video. That we wanted to limit the rise time to 0.1 seconds, limit the percent overshoot to 10% for the first jump, and limit the settling time to 1 second. We were able to do so with appropriate analyses and selection of a PID controller based on final value and steady state error analysis. We were able to make sure that the output frequency of the turbine always match the input frequency from the grid, as well as reject disturbances from the load, the power of load from the grid. In general, we decided to conduct our robustness analysis on whether or not we could reject disturbances rather than if we could tolerate delays, because in the real world, there's very little delay in the grid, and rather the quality of the control system should be judged based on the rejection of disturbances.
Here we're going to find steady state error. So the equation is the error equals 1 over 1 plus the open loop transfer function times R of S. So we already have the open loop transfer function, and we know R of t equals A times the unit step function, which makes R of S equal A over S. And we know that the limit of E of t as t goes to infinity is equal to the limit as s goes to 0 of the error function times s. So we have the error function, and we're going to plug in R of s and distribute the a out, and then we're going to move the s to the other side to get us E of s times s. And then we're going to take the limit of that once we've simplified that equation, as shown here. Once we take the limit, everything with an s is going to go away, so this, and then all of this here, which will give us d times a over ki plus d, and we want this to be close to 0 as possible, so to minimize this, we need to make ki large. To find the final value, we first have to neglect disturbance. So to neglect disturbance, we just remove this part of the equation. You can move this over here if you want to get ws over r of s. That gives us that equation there. And we know that the limit as t goes to infinity of the system frequency is equal to the limit as s goes to 0 of ws times s. So we're going to go ahead and set that up. So for response to step input, r of t will equal a times the unit step function. And we know that r of s should equal a over s, and a is just an arbitrary input. Okay, so plugging that into our equation here, we get ws equals the original stuff in the parentheses times a over s. Now, if we move that s over, we get ws times s, which is what we want to take the limit of. So we're going to go ahead and take the limit, and everything with an s is going to go to 0. So all that goes to 0, and that leaves us A times Ki over Ki, which is just A times 1, so it just equals A. So that shows that neglecting disturbance allows the response to follow whatever reference frequency we give as input R of S. So we're going to find Kd, Kp, and Ki. So here we have our transfer function. We're going to take the denominator and divide out the coefficient in front of s squared across the whole equation to get this, which gives us omega is equal to the square root of Ki over Kd plus 2/8 times h. And we know h is equal to 4, d is equal to 5. Those are our presets that we found previously. And we're going to iterate to find Ki by using the rising time specs of 0.1 is equal to 2.2 over our omega. Plug in our omega equation. We're going to get Kd is equal to 10 and Ki is equal to 8,712. For the settling time specs that we're going to use to find Kp, we know the settling time is equal to 4.6 over the entire omega frequency for n. So our settling time should be 0.3 seconds, which is then equal to this equation here, and our total omega is going to be Kp plus d over Kd plus 2h, all over 2 times omega, but the omegas cancel, which just gives us this then on the denominator, and solving for Kp, we then get Kp is equal to 470.